Welcome to this explainer. Today, we're diving straight into the engine room of speech recognition. We're going to uncover exactly how acoustic models actually learn to map raw audio to text. It's honestly one of the most fascinating processes in all of machine learning, but it's built on a massive, fundamental contradiction that researchers had to very cleverly engineer their way out of. Let's get started.
We've got a lot of complex ground to cover today, so here is our roadmap. We'll tackle the alignment paradox, contrast decoding with training, break down the hard EM loop, see exactly how it powers hybrid neural networks, compare it to its famous cousin Balum-Welch, and finally look at the modern end-to-end shift.
All right, part 1, the alignment problem. Imagine you're building a speech model. You've got an audio file of someone speaking, and you've got the text transcript of what they said. Sounds like a perfect setup, right? But here is the massive roadblock. To actually train the model, you absolutely must know which specific fraction of a second of audio, the audio frame, belongs to which specific hidden state or phonetic sound. But you don't have that. That frame-by-frame alignment is completely hidden from you. You know the words, sure, but you don't know the exact millisecond where one sound ends and the next begins.
It is a literal chicken and egg scenario. We call this the circularity paradox. You're stuck needing the exact thing you are trying to build. Think about it. You need an already trained model to accurately guess how the audio aligns with the transcript, but you absolutely need that exact alignment to train the model in the first place. Talk about being stuck.
Moving on to part 2, decoding versus training.
Before we fix that paradox, we have to clear up something that trips up so many people. It's the difference between decoding and training, even though they use the same search under the hood. Decoding is what happens at test time. Your model is totally fixed, and finding the single best state path gives you your final transcript. It answers what was said. Training, though, is a different beast. At train time, the path you find isn't the final answer at all. It's just used as a temporary intermediate label so you can update the model's parameters. Same search, completely different purpose.
Which brings us to part 3, the hard EM loop. So how do we actually break out of that circularity paradox? Well, basically by faking it till we make it. This is the famous loop. Step 1, you align. You use your current flawed model to guess an alignment. By constraining the Viterbi search to the known transcript, you force the model to generate a hard label for every single frame. Step 2, you update. You take those guesses and re-estimate the model's parameters. And step 3, you repeat. As the model improves, the alignment gets better, which makes the next update even better. You just iterate until the whole system stabilizes.
This brilliant iterative process is formally called hard EM, expectation maximization, and that word hard is absolutely crucial. It's called hard EM because the algorithm does not hedge its bets. There's no waffling. It commits entirely to the single best path found by the Viterbi search to create absolute definitive labels for every single audio frame.
This quote perfectly captures the vibe of Viterbi Training. No uncertainty allowed. The algorithm emphatically decides. Frame 5 is state K2. Done. It doesn't care at all if there were other mathematically possible ways to align that frame. It just picks the winner. And by committing so early and so definitively, it makes the training process incredibly fast and computationally cheap.
Part 4, powering hybrid neural networks.
Now, you might be wondering, why does this classic loop still matter so much today? It matters because Viterbi Training is the essential bridge that makes hybrid neural networks possible. Look at the standard DNN-HMM recipe. First, you force align the audio using an older, simpler model. Second, you use that Viterbi search to label every single frame. Third, you take those hard labels and use them as the exact targets your deep neural network is going to learn from.
Without this forced alignment step, your deep neural network would be completely lost. Deep learning thrives on labeled data, right? Viterbi forced alignment is the magic wand that takes huge amounts of continuous, unlabeled audio and converts it into discrete, per-frame targets, specifically senone targets. It's literally the invisible scaffolding holding up the entire hybrid neural network architecture.
All right, part 5. If you have a machine learning interview coming up, pay attention because they love to ask about this. Viterbi versus Balum-Welch.
This is the ultimate showdown. On one side, Viterbi Training, your fast, hard EM approximation. It finds one best path, assigns exactly one state per frame, and is super cheap to run. On the other side, Balum-Welch. This is the soft EM approach. It considers all possible paths at the same time, weighing them by probability. It fractionally shares frames across states. Yes, Balum-Welch is way more computationally expensive, but because it keeps that mathematical uncertainty alive, it usually gives you a slightly more accurate acoustic model.
At the end of the day, the absolute core mathematical difference boils down to a single operator. Viterbi uses the max operator. It just looks at the previous states and takes the maximum value to find a clear winner. Balum-Welch, acting as the forward-backward algorithm, uses the sum operator. It adds up the probabilities over all possible paths to get the total likelihood.
To put that in plain English, Balum-Welch allows for fractional sharing. It whispers, well, I think frame 5 is maybe 70% state A and 30% state B. But Viterbi slams its fist on the table and demands absolute certainty, declaring frame 5 is state A, and we are moving on.
Finally, part 6, the end-to-end shift.
It's wild to look at how the field has swung back and forth like a pendulum. Phase 1, the classic era, we relied on Balum-Welch, soft, sum-based math for GMMMs. Then Phase 2 hit, neural networks needed massive amounts of data, so we shifted to Viterbi training, hard, max-based alignments for hybrid DNNs. But now, in Phase 3, modern end-to-end models have swung the pendulum right back to soft, sum-based mathematics, largely thanks to CTC loss.
CTC loss, connectionist temporal classification, was a total game changer. By returning to a soft, sum-based approach that calculates probabilities over all possible alignments internally, CTC completely shattered that circularity paradox we started with. Because it does this directly inside the loss function, you don't need a separate, hard, forced alignment stage anymore. No more guessing, updating, and repeating in a disconnected loop. The model just figures it out.
So, this leaves us with a truly fascinating question. We've journeyed from soft probabilities to hard Viterbi labels and back again to end-to-end internal summations. With modern models beautifully handling alignment internally now, has the elegant, hard-committing logic of the Viterbi training loop permanently handed the baton to soft end-to-end systems? It is a profound shift in how machines learn to listen, and absolutely something to keep in mind as you dive deeper into the world of AI. Thanks for joining me on this explainer, and I'll catch you in the next one.